Welcome to this lecture. This is the second lecture of week 2. In this week, we are discussing connections of lower dimensional measures with higher dimensional measures. In the first lecture, we have talked about the connection of the Lebesgue measure in one dimension with the Dirichlet measure on the two dimensions. Now, using that, motivated by this example, we wanted to construct the measures in higher dimensional spaces using lower dimensional measures. And to do that, we started by looking at two given measure spaces and described a product sigma field on this product type sets. In this lecture, we are going to talk about constructing a measure on this product sigma field. Without further delay, let us move on to the slides. So, let us recall the setup once more. So, we are working with the connection between the Lebesgue measure on 2 dimensions and the Lebesgue measure on 1 dimensions, and with this we have described these product sigma fields on product type sets, and let us see how we can construct a measure on this product sigma field. Again, we set up the notations first. We take omega 1 f1 and omega 2 f2 to be two measurable spaces. We already have described the product sigma field f1 tensor f2, which is generated by the product of the collections. First, we describe important construction of sets coming from the product sigma field. We call this as sections of a set in f1 tensor f2. Here, we start off with any arbitrary set capital E in the product sigma field and choose a point in the first set, call it small x. Then what we can define is a section of the set E corresponding to the point small x, and we write it with the subscript. Similarly, if we choose a point y in the second set, then again we will describe a set which we will call as the section of E with this second point y. And for the notations that we are following from the first lecture also is that choosing points from the first set and doing some construction with that, for that we will always denote it by the subscript. Choosing points from the second set and doing certain construction with that, for that we are going to use the superscript notation. So, let us look at the type of sets that we are going to consider. So, what we are doing is that by fixing the first point, we are asking what are these pair of points such that it is belonging to E. So, we are looking at all possible y such that the pair x comma y is in the set E. Similarly, if you look at the point y coming from the second set, you can define another such section. Here we will vary the points in the first set, and then we will look at whether the points x comma y is in the set E. Here, just to avoid any confusion, let us make a minor change in the notations that is here. We will look at all possible points t such that the point x comma t is in the set E, and we will look at all possible points coming from the first set, let us call it small s, such that the point small s comma y is in the set E. This is just to avoid certain notational confusions that you might be having, because we have already fixed points small x and small y. So, in the lecture notes finally supplied to you, I will make these corrections. So, I hope you have followed the definition of a section coming from the sets of the product sigma field. But now, let us move on. Here, what we are now going to consider are properties of the sections that we have just considered. So, let us again take any arbitrary set coming from the product sigma field and look at sections with points coming from the first set and sections coming from the second set. Here, what we claim is that these sections must be in the appropriate sigma fields, meaning E subscript x was defined as a subset of omega 2 and it must be a measurable set, and therefore, it must be in f2. That is the statement that is guaranteed by this theorem. Similarly, the section that we see by fixing points from the second set, that must be a subset of the first set, and therefore, we claim that it must be a measurable set in the set omega 1 and therefore, it must be in the sigma field F1. We are going to prove these statements. Moreover, this link with sets also extends to measurable functions. Let us explore the properties of measurable functions which are defined on this product type sets. Look at real valued measurable functions defined on this measure space. If you have such a measurable function, then consider this kind of functions by fixing again points from the first set. So, if x is a point fixed in the first set, then we can define a function only on omega 2, a real valued function denoted by f x comma dot, defined in this way that f x comma dot is a function that takes any arbitrary point from the second set to the value f x comma y. And we claim that this function f x comma dot must be f2 over Br measurable, meaning it is measurable with the domain side measurable space omega 2 comma f2 and the range side measurable space R with Br. Similarly, by fixing a point coming from the second set, we can look at another such function which we denote by f dot y. It is defined on the set omega 1 and takes real values. It is defined in this way that for any arbitrary point x coming from the first set, f dot y takes it to f x comma y, and we claim that this is also a measurable function with f1 over Br measurability, meaning this is a function is measurable with the domain side measurable space omega 1 comma f1 and range side measurable space R comma Br. Let us prove both these statements. Now recall that in lemma 1 we have already proved the measurability of this function pi subscript x, which takes points from omega 2 to omega 1 cross omega 2 by moving any point small y to x comma y. Now, if you take any arbitrary set E coming from the product type set, it is an immediate observation that the pre-image of such a set E under this mapping pi x goes like this, that it should be points of the form y such that pi x of y must be in E. But for this to happen, we must have all y in omega 2 such that x comma y is in the set E, but this is exactly the definition of the section of the set E by the point x, which is E subscript x. So, what we have just obtained is that E subscript x is the pre-image of a measurable set E coming from the product type sigma field, and pi subscript x is a measurable function that was proved in the previous lecture, and hence this pre-image which is E subscript x must be in F2. Similarly, if we use pi superscript y, that is again a measurable function from omega 1 f1 to omega 1 cross omega 2 with the sigma field, the product type sigma field. So, using this measurable function and using the identification that for any product type measurable set E, the pre-image under y will land up into E superscript y, which is the section of the set with the point y, and therefore, we will claim by the measurability again that E superscript y must be in the first sigma field F1. So, this proves the first part of this theorem that we have just stated. Now, let us look at the property involving the functions. So, here what we do first is that we fix a point again coming from the first set. Now, consider this composition of functions. First, we start with the second set omega 2, apply the function pi x, which will take it to omega 1 cross omega 2 by sending any y to x comma y. But then you again appeal to the function f which is given to you, then this will be taken to the value f x comma y. This is a real number. So, therefore, you have a nice composition of functions. Now, here let us look at this composition of functions evaluated at a point y in the domain omega 2. Here by use the definition of composition of functions. So, first evaluate the function pi x and then evaluate the function f. So, this will just give you f of x comma y as seen in the diagram above. Now, as a consequence you can write it as f of x dot acting on y. This is the function which we have described in the statement, and hence what we have just identified is that f x comma dot, that function is the composition of the functions f and pi x. But since the function f is given to be measurable and we have separately proved the measurability of pi x, therefore, the composition must be measurable. So, since composition preserves measurability, and therefore, what we end up having is that f x comma dot must be a measurable function. Now, so the statement involving f dot y we can prove in a similar way by looking at the composition of functions f and pi y. This completes the proof. So, this is a very important theorem that connects sections of a set and measurability of it, and also the kind of a projection of the two dimensional functions to one dimensional functions. Now, we will use this result in our construction of the measure. So, now we start off with two measure spaces, one which is omega 1 f 1 mu 1, another is omega 2 f 2 and mu 2. Here what we want to do is to construct a measure on this product set omega 1 cross omega 2, but with the product sigma field in action. But then we also want to use the information from the individual measures mu 1 and mu 2. Essentially, by using this information from the lower dimensional measures mu 1 and mu 2, we want to construct a measure on the product sigma field. In what follows, to make our exposition easier, we will take mu 1 and mu 2 to be finite measures. Now, state the next result without proof. This result essentially uses standard measure theoretic arguments, and this can be proved in standard approach. Let us start with any arbitrary set coming from the product type sigma field. Now, look at this function which sends any point small x from the first set to this number which is mu 2 of Ex. Remember, the section set which is Ex, we have already justified that it is in the sigma field f2, and therefore, we can talk about the mu 2 of this set. So, this gives you a number in the real number, this gives you a number which is non-negative in fact, but just for the exposition we just go with real numbers. Now, this is a function that starts with omega 1 as its domain and goes to real line in its range. We claim that this must be f1 over b are measurable, meaning this function is a measurable function with the domain side measurable space omega 1 f1 and the range side measurable space as r br. Now, similarly, we can describe another function from omega 2 to real line by sending a point y to mu 1 of Ey. Here what we are using is that E superscript y is a set in f1, and therefore, we can talk about mu 1 of E superscript y, and we claim that this is also measurable, but with the measurability structure given by f2 over br, meaning the domain side measurable space is omega 2 f2, range side measurable space is r br. The proof of this uses, as I said, standard measure theoretic techniques, and we skip this for brevity. Now, let us move on and look at certain measurable function structure on the product type sigma field. Now, this non-negative measurable functions that we have already obtained in this theorem, we can define this non-negative set function. So, let us go at it slowly. So, what we do first is that we look at two functions which we call as P1 and P2. This we define on the product type sigma field f1 tensor f2, and we define them so that they become non-negative, but they might also take the value plus infinity. Let us see how we can define them. So, start with any set capital E coming from the product sigma field, then associated to that we look at this number. First, we look at mu 2 of Ex for any arbitrary point small x in omega 1. We have just understood that x mapping to mu 2 of Ex is a measurable function on omega 1, and therefore, we can integrate it with the first measure mu 1, and therefore, since the integrand here is non-negative, the integral value will also be non-negative, but it might be plus infinity. That is how we are getting the number P1 of E. In a similar manner, we look at P2 of E. Here we first look at, for any arbitrary point y coming from omega 2, the number mu1 of Ey. Here what happens is that the function y mapping to mu1 of Ey is measurable and we integrate it against the measure mu2. But since the integrand is non-negative, again this integral is non-negative, but might take the value plus infinity. That is how the function P2 of E is defined. Now, both of these P1 and P2 actually turn out to be finite measures. This can be checked because mu2 of Ex and mu1 of Ey dominated by these quantities and these quantities. These two quantities are given to be finite. Now, mu1, the maximum value attained will be this. For mu2, the maximum value will be mu2 of omega 2. So, now if you apply these bounds in this above integral, you will immediately have the bounds for the functions P1 and P2. So, therefore, what you end up having is that actually P1 and P2 turn out to be finite measures on this product sigma field. Moreover, if you look at these very specified product type sets which are of the form A cross B, A coming from the first sigma field and B coming from the second sigma field, then you can notice this very important structure that the section of these sets are of a very specified structure, meaning here if you choose the point coming from the first set, then you will have B, otherwise you will have the empty set. Similarly, for the section with respect to the point y, you can make a similar observation. Now, if you look at this very specific product type sets E, then P1 of E we can simplify according to the formula given to us. Now, mu2 of Ex is mu2 of B whenever the point x is coming from the set A, and therefore, you will have this simplified looking integrand. Now, let us work it out and you will end up having this number mu2 of B times mu1 of A. So, P1 of E actually turns out to be mu2 of B times mu1 of A provided E is A cross B. You can do a similar calculation for P2 of E and you will end up with the same number once more. You will end up with the same number once more. And therefore, what you end up having is that P1 of A cross B agrees with P2 of A cross B, and that value is mu1 of A times mu2 of B. But here A and B are arbitrarily chosen from F1 and F2. Now, these type of sets A cross B are actually generating the product sigma field, and therefore, what we end up having is some kind of a uniqueness identification for the functions P1 and P2. These functions P1 and P2, remember, they are defined as integrals of certain non-negative functions and they are associating certain numbers to sets. So, therefore, they are actually have the structures of finite measures. But now, we make this very important identification that since these measures agree on the product type sets which generate the product sigma field, therefore, if you take any two such measures which are given to be finite measures, then there exists a very unique finite measure on the product type set with the property that it actually associates this exact number as the size of the product type set. Now, you can further extend by uniqueness to the whole product sigma field, and here this function P is essentially either the function P1 or the function P2, and both agree on the product type sets. The existence, as I just pointed out, is essentially following by looking at either of the measures which coincide. But now, this is giving you the existence. You can appeal to the generating sets approach and identification of measures on top of such generating sets, and you can get the uniqueness by standard measure theoretic techniques, and this part is left as an exercise to you. Please complete this part of the proof. But now, we want to actually further justify that the function which we are talking about, the function P, must be finite. To do that, what you do? You look at the P of omega 1 cross omega 2, which is the largest possible set that you can see. But then as per the properties, it will be mu 1 of omega 1 times mu 2 of omega 2, both of which are given to be finite, and therefore, this P turns out to be a finite measure. This completes this construction, and this is what we are going to refer to as the product measure. So, let us continue with the notations of this earlier theorem, that we have two measure spaces given to us, omega 1 f1 mu 1 and omega 2 f2 mu 2. On omega 1 cross omega 2, we have the product sigma field f1 tensor f2, but now we have constructed a measure on this product sigma field, and this is what we are going to call as the product measure of mu 1 and mu 2, and we will denote it by mu 1 tensor mu 2. Now, several points about this product measure are important, and we highlight them one by one. If these two measure spaces, which we have originally taken to be finite measures, actually turn out to be sigma finite, then the similar construction can be worked out, and appropriate justifications will be required to justify the appropriate sigma finiteness, because on the product sigma field, the product measure that we will get will actually turn out to be sigma finite. Now, it will still continue to have this identifying property that on product type sets A cross B, the size that it associates is mu 1 of A times mu 2 of B. Moreover, what you will end up having is that starting with these sigma finite measures, you have another sigma finite measure on the higher dimensional space omega 1 cross omega 2. This should remind you of the earlier example that we have been studying in the previous lecture. Now, this earlier identification of the Lebesgue measure in 2 dimensions can now be restated using these notations that we have just introduced. It is that the 2 dimensional Lebesgue measure is exactly the product measure of Lebesgue measure in 1 dimension with itself. Now, with this construction, we can repeat it finitely more times. So, if you are given sigma finite measure spaces omega j, f j, mu j for j from 1 through n, then we can repeat this construction, and using this associativity of the product sigma field that we have discussed in the previous lecture, we can also justify the construction of product type measures on this product sigma field, and therefore, we will again end up with a sigma finite measure space. In particular, you can repeat this identification on the usual Euclidean spaces, and we end up having the fact that the Lebesgue measure on the n dimensional space can be identified as the n-fold product of the 1 dimensional Lebesgue measure, meaning the Lebesgue measure on the real line. So, if you take the n-fold product, you exactly get back the Lebesgue measure in the nth dimension. Moreover, there is a very important property that we will be using in our follow up lectures. It is that if you start off with probability spaces, so remember we have been so far working with finite measure spaces or sigma finite measure spaces, but let us restrict our attention to probability measures now. If you take 2 such probability spaces, then you end up with this product type structure that we have just introduced. Now, here we claim that the product measure that we will have will be a probability measure, and therefore, the product measure space that you end up having must be a probability space. To verify this, all you have to check is that P1 tensor P2 associates the mass 1 to omega 1 cross omega 2. To see this, use the properties of this product measure. All you will have is that P1 of omega 1 times P2 of omega 2. But since both P1 and P2 are probability measures on omega 1 and omega 2 respectively, both these values are 1, and therefore, you end up with 1, and therefore, P1 tensor P2 will actually be a probability measure. We now work with sigma finite measures in generality, which will now continue to denote by omega 1 f1 mu 1 and omega 2 f2 mu 2, and we focus on integration with respect to this product measure. Remember, we already understand how the measurable sets look like in this product sigma field. We also understand how measurable functions look like, and we have essentially discussed it through these properties through projections and certain sections of sets. Now, let us use this product measure and look at the integration properties. Now, here if you start off with arbitrary sets A coming from the first sigma field and arbitrary sets B coming from the second sigma field, then we have these very nice identifications. Let us start off with mu1 tensor mu2 of the product type set. Now, we can identify with the integration structure on mu1 tensor mu2 and we have to take the indicator function of A cross B. So, that is your standard identification for measure theoretic integration. But now, mu1 tensor mu2 of A cross B can now further be identified with this product of the numbers, and these are also identified with the measures P1 and P2 as we have discussed earlier. Now, if you recall these definitions of P1 and P2, then you will have to use the sections now. But remember, we are using this product type sets A cross B and we will therefore have to use the sections of A cross B with point x and point y coming from the first set and the second set respectively. And then if you recall the definitions of P1 and P2, then you will end up having these expressions at hand. But now, inside these integrands that you will have, these are also measures of these sections, and therefore, you can actually revisit all of this in terms of these iterated integrals. Let us you take a few minutes and let us understand these structures. What we are saying is that let us look at the product type sets A cross B and integrate this indicator with respect to the first measure. That will essentially give you the mu2 of the section of A cross B by the point x. And if you integrate it further with the measure mu1, you will get this iterated integrations which will give you the function P1. Similarly, you will get the function P2 if you reverse the order of the integrations in the iterated integrals. First integrate out with respect to the measure mu1 and then integrate with respect to the measure mu2. Now, for this product type sets A cross B, what we have identified is a connection between P1, P2 and mu1 tensor mu2 as we have constructed. Now, let us write it in another notation also, because it is the product of the numbers in mu1 of A and mu2 of B. Therefore, we can separately write them in terms of these integrals over one variable. One is over the variable x, another is over the variable y. Now, this identification that we performed for the indicator of A cross B can be repeated for multiple such product type sets AI cross BI. So, here what we do, we first choose certain non-negative scalars alpha 1, alpha 2, alpha 2, alpha n, and we choose these sets A1 and 2 an from the first sigma field, B1, B2, Bn in the second sigma field. And therefore, we can look at indicators of AJs cross BJs. Now, if you look at these linear combinations with these scalars acting as the weights of the linear combination, then if you use the previous relation that we have just justified and take essentially the summation of the relations, you will end up with this relation, that summation over this integration with respect to the product measure mu1 tensor mu2 can be written as summation over certain specific iterated integrals. In one direction you can integrate with the second variable first and then do the integration with the first variable, and in another direction you can integrate out the first variable and then integrate with respect to the second variable. And in this case what we are saying is that linear combinations with positive weights for these indicators gives you this interesting property that you can perform the integration with respect to the product measure, but you will get the same value if you were to perform the iterated integrals with respect to the either of the lower dimensional measures mu1 and mu2. This leads us to a very important observation that calculations of integrals using the product measure can actually be performed using iterated integrals, and this is helpful because if you want to perform an integration in higher dimensions, then if you know that your higher dimensional measure is actually a product measure, then maybe you can reduce it to iterated integrals and which will be on lower dimensional spaces, and the integrals that you will have to perform will be on lower dimensional spaces only. That will reduce the computational complexity. Since we have verified this relation for simple looking functions, meaning for positive combinations of indicator functions, therefore, we actually have it for non-negative simple functions, and therefore, using the fact that these sets of the form A cross B generate the product sigma field, we claim that for non-negative measurable functions we will be able to extend this result, and we will end up having the fact that for a 2 variable function, if we integrate with respect to the product measure mu1 tensor mu2, then we can perform the same integration through iterated integrals, either integrate out the second variable first and then perform the integration with respect to the first variable, or if you wish you can perform the integration with respect to the first variable and then the second variable. This leads us to a very important result, and this is what we will try to generalize. Now, this was for the non-negative measurable functions, we take it to general measurable functions by usual measure theoretic techniques. But here we have essentially used this fact that small x mapping to this integral and small y mapping to this integral are measurable functions. These are essentially extensions of the ideas that the measures of sections actually give you certain measurable functions. This we have already seen. This is the generalized version of the results. Now, these calculations for non-negative measurable functions we will be extending using standard measure theoretic techniques, and these natural extensions can be done for measurable functions, but as you can understand with certain appropriate integrability conditions. And this consolidated statement is as follows. We skip the proof for brevity, and as said earlier, this uses standard measure theoretic techniques. This result is called as the Fubini-Tonellis theorem. Here what we have is that we start with two sigma finite measure spaces, omega 1 f1 mu1 and omega 2 f2 mu2. Here we will start off with this two variable function defined on omega 1 cross omega 2 and assume that it is a measurable function on this product type space. Now, if this is a measurable function, then the first case is the non-negative case. Here what we have already discussed is that the equality star holds. So, let us just recall what this equality was all about, that the integral of the function f with respect to the product measure which is on the product set omega 1 cross omega 2 can be performed using iterated integrals. First you integrate out one of the variables and then you integrate with respect to the other variable. So, this is a very important equality which will helping us in reducing the computational complexity of the higher dimensional integrals and then bringing it down to lower dimensional spaces. Here if we now are going to extend it to general measurable functions, then let us work with integrable functions with respect to the product measure. Here if it is integrable with respect to the product measure, then we first claim that there exists a mu1 null set capital A and a mu2 null set capital B, such that first for points coming from the complement of this mu1 null set, you can look at this finiteness of the integral when you integrate the function with respect to the second measure. Similarly, if you choose points coming from the mu2 null set B complement of that, if you choose such points in the complement of the mu2 null set B, then again you will have the finiteness of the integral of mod of f when you integrate with respect to the first measure. Now, using this you can look at integrals of them and look at the iterated integrals as we have been talking about, and we finally claim that if you have the L1 integrability with respect to the product measure, then the equality star holds, meaning you can write down the integral in the joint variable with respect to the product measure. You can reduce it to integrals involving iterated integrals, meaning you perform the integration with respect to one of the measures first and then perform the integral with respect to the other measure. We will sometimes refer to this Fubini-Tonless theorem as simply as Fubini's theorem. This is just for the sake of ease of notations, and in the next lecture we are going to discuss several important applications of this Fubini's theorem. So, in this lecture what we have done is that using the product sigma field that we have already seen, we use the underlying measures to construct a measure on the product type sets on the product sigma field, and we have also identified several important properties of sections of the sets and of jointly measurable functions. And finally, what we have obtained as the main result is justifying that the integral with respect to the joint variable, meaning with respect to the product measure, can be reduced under appropriate integrability conditions to integrations involving iterated integrals, meaning you integrate out one of the variables first and then perform the integration with respect to the second variable. We will see several applications of this, as I said, in the next lectures. Let us stop here. Thank you.